Welcome to the first episode of AE Live, a podcast from Associated Engineering. Associated Engineering has been a leader in engineering since 1946, and with this podcast, we're bringing you an inside look at what it's like to work with a Canadian consulting engineering company. We'll tell you some stories of projects, past and present, and we'll sit down with our engineers, scientists, and technologists who will share their insights and experiences. My name is Graham Nix, and today's podcast is all about new beginnings.
Coming to you on the internet audio, all the STEM homies know he's where you gotta go, vibing your ride to the Graham and Michael groove. Whoa, it's a whole new funky flow and treat your ears, get the gist of careers from the list of our engineers and scientists, maybe twist it up with technologists. It's a podcast, baby, and not to be missed. Got more fly than a ripe banana, like Sam, I got the stamina streaming across Canada. I can treat Sugar Band, I got that swaggity swag, yeah, and the 411 from Whitehorse to Niagara. Don't you know we're gonna innovate? Got a topic here to elevate. Gonna entertain and educate.
Whether it's new beginnings in engineering to newly starting out in your career, or developing a new specialty within your career, it's never too late to start something new. My guest today will be Don Kennedy. Don is retiring after a 40-year career in engineering, and we'll talk about beginning his career, some memorable career highlights, and what it's like to begin his retirement. This podcast is recorded in Vancouver on the traditional, ancestral, and unceded territories of the Coast Salish peoples, including the Musqueam, Squamish, and Tsleil-Waututh nations. On the topic of new beginnings, humans have been building things for thousands of years. Ancient Earth is dotted with magnificent structures built by people and civilizations that are long gone. Let's look back a bit on the ancient works of engineering that cover our world over the course of this podcast. One example comes to us from ancient Egypt. Imhotep, a name people will recognize from movies and stories and popular culture, is considered to be the architect of the first known step pyramid in Egypt. Rising 61 meters from the desert floor, Imhotep's six-step pyramid, built for King Zoser, is the oldest existing monument of hewn stone in the world, having stood for over 4,500 years. Was Imhotep the world's first engineer? We'll introduce a few other ancient wonders as we go on, but now I'd like to introduce Don Kennedy. Don has worked with Associated Engineering for over 25 years. He has a civil engineering diploma from BCIT and engineering degrees from Lakehead University and McMaster. He's been the director of the Canadian Association for Earthquake Engineering, and he finishes his career as Vice President, Transportation Structures at Associated Engineering. Don, welcome to the podcast.
Thanks, Graham. Yeah, nice to be here.
So, Don, we thought we'd launch our new podcast by talking about new beginnings. Take me back to 1982 and Lakehead University. What does a young Don Kennedy think his future career is going to look like?
Oh, all the way back then. Well, when I graduated, from, with a bachelor's degree going into engineering, civil engineering, that was a time of, high uncertainty what my career was going to look like. And I think that's probably quite common for lots of graduates, with bachelor's degrees. I didn't know how many of my skills from university would transfer to work, how prepared I was. There was a lot of uncertainty, so there was, some fear or, apprehension about what the career and what the jobs were going to be like. I did have one advantage that I always felt for myself, and some graduates will have it and some won't. I was pretty clear that I was interested in structures. I was in civil engineering, which is a lot of different things. Structures, transportation, water, wastewater. It's a lot of different things, geotechnical. But I was pretty interested in structures. So at university, I took some electives along those lines. So when I graduated, even though there was uncertainty and apprehension, I had a certain confidence that came from knowing what it was that I was interested in, what I wanted to pursue, and I think I was, quite well prepared from my undergraduate studies. That's not always going to be true for a lot of graduates, civil or any engineering. They're still very much exploring what it is they want to do. So from that perspective, my early days were different, and I have a lot of sympathy for young, graduating engineers. I've got, two sons that are graduated from engineering, and they have to sort out what they're really interested in and what their career is going to look like. So I can see them going through that right now. And so that's a difference between myself and some. But engineering is an opportunity to explore a lot of different things. If you don't know what your passion is right now in your early stages of your career, it's because you're not supposed to. It's quite normal, and you shouldn't be too concerned about that. And things will unfold in an interesting path, and I'm sure.
Sounds like a good piece of advice for any new graduate. Do you have a sense then of what differences in terms of challenges you faced, in the early 80s, and what challenges a new graduate is facing today?
I did go on a little bit later after a couple of years of engineering work. I mean, when I started out as 2 years, became a professional engineer, and then not long after that, it became 4 years. But there's a lot more knowledge, a lot more specialty, a lot more specialization. It may be that when as you begin to find a path of interest, it could be that engineering is lifelong learning. We told you that in the early days of your university. We told you that at the Iron Ring ceremony, and here you are. So the lifelong learning is a really big part of engineering. So whether it's a little bit of grad studies or courses or reading journals, things like that, that's for you to do to advance your career. And I think that was important at the beginning of my career. I think it's at least as important, possibly more important now, because there's so many different areas of specialty and so much knowledge being added. But there's so much more. There's so many more areas of interest that are new. Climate change, resilience, and design, and uncertainty, and risk. There's really is a lot more opportunity for really bright, original thinking, passion. Multidisciplinary thinking about things, design thinking, working with others. Engineering sometimes is working in your cubicle, but more often than not, it's collaborating. So I think that's become more important, in recent decades.
Right. You mentioned you have 2 kids that have followed you into the engineering career. Did you have any advice for them that you'd want to pass on to more people if you could?
I think the lifelong learning part, I think they picked a very good path. It's got every likelihood of being challenging and impactful and successful. So, explore. I've encouraged them to keep exploring for the next few years, even though I started out with an early interest. Most people, I suspect, are they're going to want to explore different areas and find things that interest them. So I've encouraged them to be not too concerned about a specific path too soon. Like, enjoy the opportunity that you've got to explore for a little while. And it never really stops.
Right.
Yeah.
So how did you find your way into a consulting engineering company?
I knew I wanted to design. And so looking for a job in 84 when I graduated was banging on doors, mailing letters, delivering letters, and looking for a job. They told me at the university, career counseling and that, looking for a job is a full-time job. I used to go to the Journal of Commerce and look at construction projects that were being tendered and things, but that would give me some information about companies that were designing projects that I might be interested in. So I just pounded the pavement, went to companies, delivered resumes, and made a bit of a pest of myself. And I was always amazed at how many people would take a few minutes to come and talk to me. Now you're submitting resumes, over the internet, and you're just sending them all out and into this big black hole, right? So it was a very different process. I preferred the personal process that I took in those days. So that I knew it was consulting engineering companies because they do the design. That's what I was looking for. I considered contractors because I was a tradesman. I was a carpenter before engineering. But I also knew that would involve moving around and maybe a much more difficult work-life balance. So it just wasn't for me. And I knew I wanted to be in Canada, in Vancouver. When I went to grad studies, learned about earthquake engineering and seismic design, but I also learned about high-rise design and offshore oil structure design, which is interesting, and it was interesting, but I knew I didn't want to go to Chicago, New York, or LA. I wanted to go to Vancouver.
Right.
And here I am.
So you joined Associated Engineering back in 1997.
Yeah.
25 years later, what were those early days with Associated like?
They were excellent. I was in New Zealand from 94 to 97. So in the 80s, late 80s, early 90s, was practicing bridge engineering in British Columbia, and then went to New Zealand for 3 years. So David Harvey and John Fussell stayed in touch with me while I was in New Zealand. So we did decide to come back to Canada. I wouldn't ever have left New Zealand to come back and just pound on doors again. But David and John had, at Associated Engineering, they had a bridge group that they were growing. They had a vision. They knew what they wanted to accomplish. And I saw a possible career path for me at Associated with the folks that were here, and then Alfred and Julian and, a number of others. Early days at Associated Engineering were extremely, interesting. We started to pursue bridge retrofit projects, big bridge projects. There was just all sorts of opportunity within bridge engineering at that time, and I'd say that we grasped it and really expanded our bridge practice. So the ability to help contribute to that in seismic and retrofit and rehabilitation was extremely interesting.
Was there a project, a specific one in those early days that really grabbed your attention, or just?
There was, and it's led to many, many others. But the first one that we competed for on the seismic retrofit side and rehabilitation side was the Mission Bridge over the Fraser River, the seismic retrofit of that project. And in the first round in the 90s, there was Oak Street, Queensboro, and Portman Bridge all got looked at by different firms, and I was involved with one of those with Crippen and CBA. And then came back to Associated 97, and Mission came out. So we competed hard. We wrote a proposal, competed hard, and we won that. And it was interesting and gratifying that we won it against the big established firms. And they were very annoyed that we won it. And we were very pleased to have won it and went out and celebrated with some of our partners from San Francisco and back east that were part of our teams. So that project was the first big project, and it established us in a different market, a bigger bridge market and a specialized and a more sophisticated market, and it opened a lot of doors for Associated Engineering's bridge practice. So that one sticks in my mind.
Do you still see opportunities like that for consulting engineers to, join a company and break into a new area? Or is it dominated now by bigger players and bigger teams and established names?
I thought seismic design would be really interesting for 5 years, and then it would become established, and then it would be commodity, and it would all be done. That hasn't happened. It's still a very challenging and evolving area of practice. And it's extreme events, and there's the earthquake in Turkey, and there's been earthquakes around the world. Our society still needs very high level of expertise and skill in earthquake engineering. Climate change, designing bridges and transportation for climate change. Extreme events, emerging extreme events where you can't use the old probabilistic frameworks, the old rules. There's a lot of opportunity for innovation in new areas. Can Associated Engineering compete with the 30, 40, 50,000 employee firms, international firms? Some markets, some projects where there's just not a chance that we're going to be doing that. There is a lot that you could pursue and gain experience with and contribute to across Canada, maybe into North America a little bit. Just depends what Associated Engineering's growth aspirations are. But yeah, there's still lots of opportunity in energy, alternative energy. We have to re-engineer our civilization. We're built on fossil fuels, and in 40 years, it's not going to be built on fossil fuels. That 40 years is a career.
Right.
A lot, people that are listening to this, what they're doing now and what they're going to be looking back on at the end of their career is going to be amazing.
What of those changes have you seen over your 40 years in your career? So, what are there technological changes that are just really changed the way you do things? And
that's an interesting question. A lot of it is, the similar tools. We could talk about BIM and 3D and new manufacturing, new construction methods, modular methods, and things like that. We have to build a lot of housing. There certainly are new tools and new challenges in 3D and things like that. Artificial intelligence is coming in. I mean, this is a very big area of change that's coming for all of us. The engineers that I work with and the projects I work on day to day after 40 years, the engineers seem similar and the projects seem similar, and the tools are a little bit different, but the need for good thinking, good engineering thinking, and innovation, a lot of it's still the same. We still need that. Yes, there's changes, and a lot of it's similar. I think the changes that new engineers are going to see in their careers are going to dwarf by a quantum the level of change that we saw during my career.
Right. Speaking of your career, you've done a lot of seismic retrofits. You're talking about kind of building that practice here at Associated Engineering. What unique challenges are there in retrofitting older structures and kind of making them adaptable to dangers and concerns we have now that weren't there when they were built?
So I think the key point out of that, and the reason I've enjoyed retrofit, or the reasons I've enjoyed this specialty so much, include with an existing bridge, an existing aging bridge, designed to old codes, and you're stuck with the problem. You've got this old bridge like the Misson Bridge. It's on poor soils, liquefiable soils, brittle details. It's going to perform terribly seismically, if it isn't upgraded, which we did quite successfully. But you can't change the problem. You have to deal with the problem that you're given. And so your innovations, your technology, your tools, your materials, and your approaches have to be tailored to the problem. When you're designing a new bridge, it's a bit of a blank canvas, and you can mold the problem or the solution to the problem. You have much more flexibility. If you've got a real design challenge, you can change the concept, you can change the materials, you can set that early on. And that takes a lot of experience, and Associated Engineering was particularly good at this. David in particular, when David would give us advice and we're going down a path, there were very few projects that we'd get halfway through the project and then have to change direction, because David's skills and experience were so good in his guidance. At other firms that I was at, it seemed to me you'd do a preliminary design, then you get in detailed design and you'd change it all and do it all again. I thought that was normal engineering. And I came with it to Associated Engineering and found out, no, that's just sort of fuzzy thinking in the early days. So I liked the seismic because there was a lot of opportunity for lateral thinking and new materials and new methods, but that you couldn't change the problem. You just had to deal with the problem, and you had to think it through. You had to find a way through. There was no easy answer. You just had to, work your way through it. And I always enjoyed that part of the challenge. And it's still there for bridge rehabilitation. Bridges last, we designed them for 75 years. They last 100, 125 years, and you're renewing these bridges over and over and over again. And as a, seismic, climate change, flooding, scour, my kids will probably be retrofitting my bridges later in their career if they go down a path. Somebody will be. Yeah, there's no shortage of challenges and work out there.
Has there been an interesting retrofit or solution to a problem that you came upon that you just makes a great story that you want to tell?
Probably lots. We used a lot of different new materials, carbon and glass, fiber. Seismic isolation, base isolation, which is a concept that comes from the 1970s in New Zealand. It took a long, long time for base isolation to really take off in North America. It's now, preventing buildings from collapsing and allowing them to become, remain serviceable, in Japan and around New Zealand and around the world. So it's really taken off. But to be able to have a building or a bridge with experiencing a major earthquake and ride through it on seismic isolation bearings with a concept that was developed in the 1970s, it's become much, much more complex to analyze these things. The concept is absolutely simple. And so we put that to good use in Canada, and we've encouraged it and simplified it in the codes, in the bridge codes, the seismic codes, because it's a very good way to go. It's only one way to design a resilient structure, but it's a good way. So there was a lot of testing being done in New Zealand and California and Japan and Europe in the 1970s and 80s related to earthquake resilience. And all of that testing and all of that knowledge was coming into the engineering practice in the late 1980s and early 1990s and to today. So that was quite an exciting time to be involved. Almost everything that we did was different and innovative and novel.
So I think a lot of people that work on problems, especially problems to existing structures, a lot of it becomes very theoretical. You make the change because models predict certain changes. I think climate change is very much that way. Perhaps with seismic engineering, it's much more real because those events occur regularly
Yes.
and around the world. Have you had something you've worked on either be tested by an earthquake after you've worked on it, or gone into places after the earthquake, and how has that gone for you?
That's a great question. The answer is thankfully no. We haven't had any major earthquakes that have struck any of the structures that I've designed or retrofitted. So I'm retired, I'm safe. But what have I left for, society? What have I left, behind? And were we successful? We know we were successful. For example, one of the things that when we worked on the Oak Street Bridge seismic retrofit, in the early days, I proposed that we do some half-scale testing on some existing, like from the Oak Street Bridge, build some piers with the same details, very similar materials, same poor details, and test them in the lab, and then do retrofits on them and test those retrofits. So the testing of the original as-built details showed that bridge and most of our bridges in British Columbia and the Lower Mainland were atrocious. They were brittle and weak, and they were doomed. And the retrofits that we designed and implemented on the testing, we tested 5 different retrofit schemes. Every single one of them worked extremely well. So a lot of them are tested, and so I have a lot of confidence. Another example is scour and flooding. I worked on the Coquihalla Highway, and some of the bridges that were scoured out during November 2021 atmospheric rivers, Jessica and Carolyn, and I worked on those bridges in the design phase. And I was a junior engineer. They were some of my first bridges, so I did kind of what I was told, right? But some of those bridges, when the abutments weren't on piles, and they scoured out, and the bridges were destroyed and washed away. So I learned that lesson early in my career, applied it to bridges later on in my career, had some sort of disagreements with clients and owners, like, this bridge is on a high energy river, we're going to put the abutments on piles. No, you're not, they're too expensive. Well, we have to because of this experience. So I think taking your experience from real life, real floods, real earthquakes in other countries, and bringing it into the practices, I have a lot of confidence in what we achieved.
I guess speaking of on that topic, as tragic as events are around the world when we see them happen, is it a big source of learning for an engineer who's looking at
Yes.
what happens and then trying to take lessons from it?
Yes, very much so. I mean, the one that's front and center right now is Turkey. Like 180,000 buildings collapsed or that need to be demolished. That boggles the mind. Are there lessons there? we know a lot about building design and construction. We've known about it for a long time. It's, a lot of the buildings there were built long before earthquake standards, but a lot of buildings collapsed after earthquake standards in Turkey were brought in. They know they're a seismic country, but construction practices really didn't follow through on that learning. And we've got a lot of unreinforced masonry buildings in Vancouver, the West End, along Kingsway, the city of Victoria. We've got a long way to go. The legislature building in Victoria is a big old, stone building. There's things we can do, but the lessons from real life, we've gained a lot of knowledge from that, and it's really important that knowledge is embraced by the engineers. This comes back to lifelong learning. I went down to Northridge after the earthquake in Los Angeles in '94 and toured that for a week with the Canadian earthquake engineering team. And one of the things that we learned there was, it was the worst of the worst buildings and bridges that collapsed. Modern bridges, even fairly modern bridges and a lot of buildings, they performed quite well, surprisingly and encouragingly, but all of the soils in the Lower Mainland are weak, soft, loose, and liquefiable. But we're dealing with all of that. We've been dealing with that since about 1990, and we've made major strides, so we have brought the lessons of real earthquakes and real floods into our engineering. Yeah, it's been very important.
Great. Well, thank you for sharing all of that. I know you've done a lot of work around bridge design code, seismic design.
Right.
Do you, what have you gotten from being able to contribute, I guess, to the wider community from that end of things?
Well, I think a lot of satisfaction. It's made an impact. I've seen the codes evolve. When I first got into this and first started earthquake engineering, earthquake engineering was a base shear force calculation, a one-line calculation, and then you distributed that load on your building and your bridge just as if it was wind or anything else. One line, right? That was seismic design, one line. Now it's 300 pages. Actually, that's not right. It's 100 pages, including structural and geotechnical on bridges. But that's all knowledge that's been captured from past earthquakes and testing and theory in universities. And it's good that it's in the code. What we're trying to do right now with the latest round is simplify it, clarify it. We've got the essence of it there, performance-based design, but we're just trying to make it flow much more clearly and simply. The design process, we're working a lot on that. But to see our codes go from literally a one line to being able to design buildings and bridges to be resilient under major earthquakes is very satisfying.
And do you think the next kind of area for code change and areas that need work there is going to be climate change?
I do, yes. And that process has started, but so climate change for bridges and water treatment plants and storm sewer and, storm water and flooding and water supply, irrigation, that's absolutely one of the areas of biggest opportunity for the engineering community. I was talking to John Van der Eeden yesterday, and we've got, postings out for climate scientists and climate engineers and data engineers. I think we have 100 postings out there, and there should be more. Yeah, it's absolutely a critical area. And a lot of our infrastructure is going to be, replaced during the course of a young person's career. So even though it looks like it's all built, it's all going to be replaced during your careers, and you're going to be doing it. And yeah, climate change and adaptation, mitigation to an extent, where we recognize that we can contribute to that, but there's only so much that we as engineers in Canada can do about that, mitigating emissions, but we can do a lot. We can do quite a bit, and we should do what we can, but adapting to extreme events is a really critical part of engineering going forward. Yeah.
Great. One thing on a very different tangent I was going to ask you is part of the podcast I was going to discuss some of the ancient engineered works that we find around the world. Are there any that strike a chord with you, or do you look back on what civilizations 2, 3, 4,000 years ago were able to accomplish and kind of marvel at it?
One little small interesting thing is how good the Romans' concrete was. We've just in the last year figured out why that was, which has been important for materials engineering for concrete and cement and pozzolans and things like that. We've just figured out, there's just a paper on that in the last year, why Roman cement was so successful, why it's still standing, centuries later. So that's fascinating. The engineering that went on through the 20th century, the early part of the 20th century is astounding. Going to the moon with, TI-55 calculators in the background is astounding. What people can accomplish with their brains and their intellect and sort of the most basic tools has always astounded me. I think we can solve our, most pressing problems, to do with climate change, for example. I think we can. I think that technology is an important part of that. Innovation is. Political will and belief in each other is just as important.
Great. Well, Don, I think I've taken up enough of your time today. You've spent a long career sharing your knowledge and passion for engineering. Yeah. You're retired or retiring, but you're still here in the office today. So what does your future hold?
It'll never be down to zero work. I'm still working on the codes, working on a couple of projects, seismic projects in here in British Columbia and in Ontario. Golf, skiing, family, cottage, water skiing, traveling, and my kids. I'm very glad to be where I am in my retirement. I'll stay busy.
Great. Well, thank you for joining us. Really appreciate your insight.
Okay.
We'll talk to you again sometime.
Okay. Thanks, Grant. Great. Thank you very much.
That was Don Kennedy, former director of the Canadian Association for Earthquake Engineering and Vice President, Transportation Structures at Associated Engineering. He was discussing his career and the contributions he's made to seismic engineering in Canada and around the world. We began this podcast talking about the first step pyramids in Egypt, and most of us are familiar with the Great Pyramids at Giza. But I wanted to take a minute to introduce a few other engineering marvels from the ancient world that are a little less well known. Built 4,500 years ago, the lost city of Mohenjo-Daro is the largest known settlement of an ancient Indus Valley civilization, which housed around 40,000 people at one time. Discovered only in the 1920s, the city is a designated UNESCO World Heritage Site. Located in northern Pakistan, it has a sophisticated water supply system, unheard of in similarly aged cities across Egypt and Mesopotamia. Another ancient wonder of engineering, the Lashan Giant Buddha, it stands 71 meters tall and was built almost 3,000 years ago, carved into the sandstone cliff face overlooking the confluence of 3 rivers near the city of Lashan, China. The stone Buddha is the tallest known stone Buddha in the world. Of particular note, the statue includes 1,021 coiled buns in its hair, which form part of a complex drainage system designed to displace rainfall and protect the statue from water damage. Various delays during its construction meant it took over 80 years to complete. Moving on to South America, we have 2 sites of early engineering at El Mirador, Guatemala, and Teotihuacan, Mexico. In Guatemala, El Mirador is a Mayan settlement that developed somewhere around 2,600 years ago. The site includes 35 triadic pyramids, including La Danta, which stands 230 feet tall and includes about 2.8 million cubic meters of space, as well as a complex network of roads that forms what might be the world's first highway system. Similarly aged, Teotihuacan is the home of the Pyramid of the Sun and the Pyramid of the Moon, and was probably the largest city on the American continents at its time, with about 125,000 inhabitants. The city has an impressively engineered layout, built around the Avenue of the Dead, and aligned with both celestial and geographic points of significance. These ancient works of engineering are not just wonders to marvel at, but also speak to the lasting impact engineering has on the world. These structures have defied time and remain as monuments to the people and civilizations that came before us, and remind us of how future generations will look back upon what we are building today. Thank you for joining me and staying with us to these very last words of our first episode. I've been your host, Graham Nix, and I hope you tune in again for our next episode.
Don't you know we're gonna innovate? Gonna entertain and educate. Hey, I know your rap ain't so great.